Okay, ma. So regarding our previous class, so we were seeing the problems on nozzles. So we have some more problems because we need to solve the problems with the various steam
Voice is
conditions.
breaking, sir.
Dry,
Not clearly.
so அப்படியா?
So clear-ஆ தான் கேக்குது.
Is that clear now? Is it okay? Manage பண்ண முடியுதாமா?
Okay, sir.
No, sir. No,
I
sir.
think okay. Okay. Break ஆனா சொல்லுங்கம்மா. I will switch over to some other network. Okay. We need to solve different problems in nozzles considering the superheated steam, dry steam, wet steam, solve those things. So this problem is a different state of steam, maybe a superheated steam. So we'll see this problem now. So let me first read the problem. Determine the throat area, exit area, and exit velocity for a steam nozzle to pass 0.2 kg per second when the inlet conditions are 12 bar and 250 degrees Celsius, and the final pressure is 2 bar. Assume that the expansion is isentropic and that the inlet velocity is negligible. Take Cp for steam. Cp is called specific heat. So Cp, the notation, we'll use it. Specific heat for the steam is 2.3 kilojoules per kg Kelvin. So regarding this problem, we have a convergent divergent nozzle. So since throat is given, it is a convergent divergent
Sir,
nozzle.
voice is breaking, sir.
Breaking,
to me.
yeah.
Others வந்துட்டு எப்படின்னு தெரியல.
Sir, voice clear-ஆ தான் sir
Others
இருக்கு.
okay, mama? Others okay?
Okay.
Clearer. Okay. Otherwise, யார்மா நீங்க என்ன ஒரு தடவை please log out and log in மா. Okay. யார்மா வாய்ஸ் பிரேக் ஆகுதுன்னு சொன்னீங்க? யார்மா? ஜார்ஜா.
சரி.
ஜார்ஜ் ப்ளீஸ்.
எனக்கு கேட்கல சார். விட்டு கேக்கு. யார் பேசுறதுமே கேட்கல. அப்படியே பிரேக் ஆகுது சார் வாய்ஸ்.
ஜார்ஜ் ப்ளீஸ் log out and log in. Please come. நான் திருப்பி அலோவ் பண்றேன். நீங்க ஜார்ஜ் can you hear me what I am telling? ஜார்ஜ் கேக்குதாமா?
text boxல போடுங்க சார்.
text box okay. Okay, so let him join. I will continue now. So regarding the given data here, it is 0.2 kg per second. So it is a mass flow rate of the steam. Kg per second is mass flow rate unit. And inlet conditions are 12 bar and 250. So pressure P1 is 12 bar and T1 is 250 degrees Celsius. The final pressure is 2 bar. So final pressure means it could be an exit pressure. So exit is 1 is inlet, 2 is throat, and 3 is outlet. That is exit. So P3 is 2 bar here. So we need to assume the isentropic expansion, no loss completely. So isentropic expansion means entropy remains constant. So in this case, we'll assume S1 equal to S2 equal to S3. Even if it is not specified, if nothing is specified with respect to the losses, no losses are specified. Even though this word is not coming in the problem, we'll take it as isentropic. So the isentropic condition is very important. Then only we can able to solve such a nozzles problem. So entropy S1 equal to S2 equal to S3 here. And inlet velocity is negligible. So already we have obtained the relation only after neglecting the inlet velocity. Now they are given the specific heat of the steam also. So this will be used while solving the problems. Okay. One of the formula we need this specific heat. That's why they given it 2.3 kilojoules per kg Kelvin. So now writing that data here, mass flow rate is 0.2 kg per second, and P1 is 12 bar and T1 is 250 degrees Celsius and P3 is 2 bar. Now the thing is, actually we need to find out the throat area, exit area, that is A2 and A3, and also the exit velocity. So already we have seen it. So if you want to find out the velocity, so we are finding the velocity in terms of enthalpy. Right hand side is will have enthalpy drop. So simply in any nozzle problem, we need to find out the H1, H2, H3. That's all. The enthalpy values of at inlet, throat, and exits have to be calculated. Very simple. So then only we can able to get all these parameters. So we are going to directly find out the enthalpy values at 1, 2, and 3. H1, H2, H3. That's all. Now let us try to find out the H1 first. So from our steam table now at P1 equal to 12 bar. So 12 bar pressure. So here one thing we need to see it here. In our previous problem, if you have your notes, you please refer it back. No temperature has been given with respect to the inlet conditions. Here the steam temperature is given. So whenever the steam temperature is given, so probably it could be a superheated steam, because the superheated steam will be specified only with respect to the temperature. So most probably this could be a superheated steam, but still we can confirm it whether it is a superheated steam. How do we confirm it? So again, I am going back to our Rankine cycle problem. So how do we confirm it? So we have to compare with our saturation temperature, boiling point. So if our saturation temperature, we'll be getting it from steam tables, and the steam temperature is greater than the saturation temperature, steam is superheated. So so in this way we can easily confirm it. So that we'll do it now. So any steam problem, just similar to our Rankine cycle only. If you are referring steam tables, so same way of whatever we did in our Rankine cycle. Yes, ma. Yes, please.
So the boiling point வந்து எப்படி நம்ம வாட்டருக்குள்ள எடுத்துக்கணுமா நார்மலா அங்க வேற
boiling point வந்துமா? For example, water க்கு வந்து எவ்வளவு 100 degree Celsius இல்லையா? 100 degree Celsius is 1 bar. The pressure varies, your boiling point will also vary. Okay, so 100 degree Celsius இங்க வந்து 12 bar pressure, அங்க 1 bar pressure க்கு 100. I will show you in the steam table now. 1 minute please. So now I'll let me go to our boiling point, that is saturation temperature in steam table. So we call it as a saturation temperature. Now, okay. So I'll go to the pressure tables. Now I'll take our atmospheric pressure first so that we can understand easily. So the saturation, this is the saturation temperature. Saturation temperature is nothing but your boiling point. So if we normally heat the water, so water will boil at 100 degrees Celsius. So this is the reason the temperature pressure is atmospheric pressure. Atmospheric pressure is 1.0132 bar. Even if it is 1 bar less than this value, water will boil at 99.63. So normally this is the atmospheric condition. So always the water will boil at 100 degrees Celsius. So that means the pressure, the domain pressure changes, boiling point will vary. So here they are given it as other than 1 bar. So definitely the boiling point will not be 100 here. So what is that pressure here? So that we have to see it here. So let me go to that problem now.
12 bar.
So we have pressure is 12 bar. So 12 bar pressure. So the boiling point we have to see it in our steam tables now. So I am going 12 bar now. So like that you see it here, when the pressure is increasing, boiling point is increasing there. So this is an experimental value. So we can confidently we can rely these values. So for 12 bar pressure, so 188 is the saturation temperature. So now so if I am the steam condition, steam temperature is above 188, so definitely that steam is superheated. So our temperature is 250 for the 12 bar pressure. So the temperature of the steam is 250. So definitely the steam is superheated now, because accordingly we have to refer our steam table. Superheated steam table will take it to get our H value. So now that only I have written it here. From steam table at P1 equal to 12 bar, saturation temperature is 188 degrees Celsius. Since our steam temperature T1 is greater than our saturation temperature, steam is superheated. If it is a superheated steam, so our procedure will slightly vary. We have to refer a superheated steam table, N value, we have to change it. So that it is very important. We need to find out whether the steam is dry, superheated or wet. Sometimes they will give it dry saturated steam directly. Then we can take N value accordingly. So for the superheated steam, the N value is 1.3 here. So in the usual way, so we'll write the critical pressure ratio relation, because we know only P1 and P3. For getting H2, we need P2. For that, we need to find out the P2 here. So writing the relation, P2 by P1 equal to 2 by N plus 1 whole power N by N minus 1. P1 is 12 bar here, so that we have substituting the values of N. Here 1.3, here also 1.3, N minus 1 is 0.3 here. So substituting all the values here, only the unknown is P2 here. So we'll easily get our P2 as 6.5 bar. So now we have all the pressures that the respective sections, we have the pressures now, P1, P2, P3. Now it is easy for us to proceed with the problems and also using the steam tables now. Coming to the parameter, first one is throat area. So where you have the throat area only by writing the mass flow rate relation. Mass flow rate equal to capital A2 V2 by small v2. George, the problem kama join pannachama? I hope George check பண்ணிட்டீங்களா ஜார்ஜ் லாகின்ல ஏதாவது ப்ராப்ளம் இருக்காமா
சார் ஸ்டில் வாய்ஸ் பிரேக்கிங் சார்
ஓகே ஓகே ஜார்ஜ் அப்படியா எங்கம்மா இருக்கீங்க நீங்க வேர் ஆர் யூ நவ ரூம்லயா இல்ல somewhere else
left at that sir
சரி ஓகே let him join okay so mass flow rate is the expression is A2 V2 is capital V is velocity and small v is specific volume. So we know that the condition 1 is superheated steam. So we'll directly go to the superheated steam table. So P1 equal to 12 bar and T1 equal to 250 degrees Celsius. So I will open our steam table. I will go to the superheated steam table now. So this is table 3 is specific volume alone we can take it. So table 4 will be a specific enthalpy of superheated steam now. So for the 12 bar pressure, we have 12 bar. I'll go to the 12 bar pressure. For the 12 bar pressure, so this is 250. So for 250, 2935.4. So the enthalpy is 2935.4 kilojoules per kg. So we have H1 is 2935.4. So we also need entropy also. So later we'll be using it. So that also we'll take it now itself. So S1 is we have to go on table 5, next 5. Because in superheated steam table separately it is given. I think you can able to recall our Rankine cycle problem. Specific volume, enthalpy, entropy would have been given separately. So I'll come to our specific entropy. Again, I'll take our 12 bar pressure. 12 bar pressure. So it is 250 is 6.831. So 6.831. So let us have these values now. Next step. Our condition 1 is over. H1, S1, S1 will use it later. So ultimately we need H1 that we have calculated. Now let us try to find out H2 and subsequently H3 also. So now the pressure at throat P2 has 6.5 bar, 55 bar. So that already we have known. But what is the state of a steam? Already it is superheated. So either it may, if the quality of the steam is very good, it may still exist in the superheated state. Otherwise, it may go to the dry or wet. So we cannot now we cannot say it exactly now. So what we can do it, we have to verify it. We have to verify with the steam temperature. So here again, steam temperature is not known here. That is, steam temperature at 2 is not known. So that should also be calculated now. So for calculating that one, we are going to use this one now. So a saturation temperature, boiling point, we can get it from the steam table. But boiling point and the temperature of the steam at this point should be compared. Then only we will know what is the state of a steam now. So saturation temperature, we'll get it from the steam table. So we need to get the temperature of the steam, T2. For that, we'll use the entropy of a superheated steam. So this formula we have discussed in our Rankine cycle problem. Okay, I will show you that one. Okay, so you see it here. So this formula. Okay, so superheated steam, we'll use it S equal to Sg plus Cps into ln of T superheated minus T saturation. So this we'll use it here. So by using that relation, we'll calculate the temperature of the superheated steam. T sup. Okay. So this superheated steam temperature, we'll get it now. After that, we'll see it whether the steam is superheated or not. We'll confirm it. So if we are going to proceed in that way. For that, it is 2 here, so I'll substitute 2. Okay. S2 equal to Sg2 plus Cp. This is specific heat of steam, and the ln of your T superheated minus T saturation. 2 is T superheated is 2. Condition is 2, so that I'll write it as T2 here. So now again, now we'll go to our steam table now. Actually, they asked Sg. So Sg is where it is available. Sg is nothing but if it is completely dry saturated steam. So Sg is available only in the dry. SFG, Sg is available only in the dry saturated steam table. So what we'll do it now? So corresponding to the 6.55 bar, we'll take our Sg value from our steam tables and we'll substitute it here. So I'll go back to our steam tables now. it is we have it 6.66. We have 6.55. Okay, so what we'll do it here, either we can take 6.4 and 6.6. So 6.55 we can take it 6.66. Okay, 6.6 ல கூட நம்ம எடுத்துக்கலாம், இல்லனா இது average கூட நீங்க எடுத்துக்கலாம். So the value will not vary much. Either you can take average of this one, otherwise you can take 6.6 also. So here if you see it here, our P2 equal to 6.5, 6.6. For this we'll take SG 6.73. Okay, so if you see it here, so it is 6.725. So you can take 6.725, 6.735. So we don't have much difference in that. So that value will take it 6.73. Now this is our SG. Now what about S2? So in the initial in our initial discussion, yes please.
So அப்போ 6.4 எடுத்தோம்னாலும் இதே ஆன்சர் தான் வருமா, வேற ஆன்சர் வருமா?
இல்லம்மா, 6.4 வந்து டூ லார்ஜ் இல்லையா, ரொம்ப டிஃபரன்ஸ் அதிகம். அப்போ 6.4 6.6 ஆவரேஜ் எடுத்துக்கலாம். இந்த வேல்யூ இது ரெண்டுக்கும் ஆவரேஜ் எடுத்துக்கலாம். கால்குலேட்டர்ல அப்படியே ஆவரேஜ் எடுத்து you can directly substitute it. இந்த மாதிரி பண்ணீங்கன்னா க்ளோசரா இருக்கும். முடிஞ்ச அளவுக்கு to the possible extent take closer value. 6.6 க்ளோசரா கொண்டு வர மாதிரி you can try it. அந்த மாதிரி பண்ணலாம். Two ways ma, either you can take 6.6, that is correct, otherwise 6.4 and 6.6 நோட average, இதனுடைய ரெண்டு நோட average you can take it, so that is also correct. 6.4 வந்து கொஞ்சம் lower-ஆ இருக்கும், so better average of these two, otherwise 6.6. The two ways would be accurate value. Okay, now S2 we have this, we need this value. So how do you get S2? Already in our problem the entropy is constant, so S1 whatever the value we have got it S1, so that is equal to S2, and further that is equal to S3. So directly S1 value I can substitute it here. So 6.831 is nothing but your S1 value, because entropy remains constant. So 6.831 and 6.730. Specific heat of steam is given as 2.3 ln of, and saturation temperature corresponding to P2 is 6.55 bar is 162. Again we can get it from our steam table. Okay, so if you see it, our steam table here, so it is 162. Okay, so you can either take average of this, so you'll be getting your 162. Now the only unknown is T2 here, so we have to simplify this. So what we'll be doing it here is we can just keep it here. So this here you will have 6.831 minus 6.73 by 2.3. இல்லையாமா, அப்படிதான் எழுதுவோம். So that 6.831 minus 6.73 by 2.3. So our value is 0.0439. So we have it ln of T2 by 435. Thing is here we have to substitute only in Kelvin, because we are dividing the temperature. So better always substitute Kelvin is better. If it is a difference of temperature, no problem, either you can substitute in Celsius or Kelvin. Whenever you divide the temperature, always your temperature should be in Kelvin. When you're taking a power dividing, so you must substitute in Kelvin. Now here we need T2, it is ln. So inverse of ln is log, it is log base e, so this will become exponential. Okay, I repeat again. So your ln is nothing but log base e, so it comes on this on the right hand side. Other side it will become inverse, that is anti-log. Anti-log is, it is ln of base, so it will be e power or exponential. In calculator if you use inverse of ln, so you will get e. So I'll keep it T2 by 435 here. So I'll keep my ln, I'll bring this ln on this side. When the ln comes this side, this will become exponential, so it will be e power of, directly type this exponential of 0.0439. so we'll be getting the answer. So now here the only one unknown we have it T2 here. So for T2 we get 454.52. so in Celsius it is 181.52 here. So if you know the temperature 181.52, then we'll compare with our saturation temperature. So our saturation temperature is 162. So again the steam temperature is still above the saturation temperature, so obviously the steam could be a superheated steam. So now we have confirmed it. So what we'll do it now, again we'll take our superheated steam temperature. We'll use the steam temperature, so that we can use it our we can proceed with our H2 and V2 and all. Okay, so what we'll do it now, for our T2 we have got 181.52 here. So I'll go back to our superheated steam table. I'll use that. specific enthalpy of superheated steam. So it is 181. Okay, actually you have to take it by interpolation. You have to take it by, so it is, we have 150 and 200. So it will be very accurate. You have to take it by 181 accurately. But we have proceeded with 200. Okay, 200 na proceed pannirukkom. But again I'm saying it. If I every one of 181 நம்ம எப்படி solve பண்ணுவோம்? 181. We use our Rankine cycle. We used. Can you recall me? One of you, please. 181. Suppose other than this temperature, solve பண்ணலையா? Interpolation. ஞாபகம் இருக்குலமா? Can you recall that one? So if it is, we'll take every madipom, we'll use it 150 and 200. Correct? So we'll take it for 150 and 200. I hope you can able to recall that one in our Rankine cycle. Rankine cycle பண்ண அதே steps தான் எல்லாம்.
Minus பண்ணி எடுக்கணும்.
Is formula. அவ்வளவுதான். 150 and 200. We'll take it for 150 and 200. We'll get it for 1 and we'll multiply with that. 150 இருக்குலமா 31.5 க்கு நீங்க multiply பண்ணி you can take it. But we have proceeded with 200. So there may be slight deviation in the answer. But நீங்க 181 க்கு பண்ணீங்கன்னா it would be very very exact answer. Okay. Now let me proceed with that. From our superheated steam table, we have taken it for 200 degrees Celsius. So our pressure எவ்வளவுமா 6.55 இல்லையா? So we'll take it here. இங்க பாத்தீங்கன்னா 200 2846 6.55. Okay, so we have 6 and 7. So இதனுடைய average value 6.7 இதுக்குள்ள இருக்கணும். 2849.5 2844.2. So இதனுடைய average we have taken it here 6.6 to 7. So average எடுத்தா நம்ம ஒரு 6.5 வரும் இல்லையா? So our 6 and 7, it will be a 6.5 here. So the average of this we can take it. So it may be closer to that the pressure which we require, which is at 6.5 bar. So for that we have taken H2 as 2846.9. Similarly, we need to take our specific volume also, because in our formula m dot equal to A2 capital V2 by small v2 is there. Small v is specific volume. So that should also be taken corresponding to the pressure of 6.5 bar. So what we'll do it, we'll go back to our specific volume of the superheated steam. So the pressure is again 6.5 bar. So we have to take it. So 0.35 to 0.299. Average of this we'll take it here. So 0.3255 metric per kg. So now we have obtained our H1 H2 from our steam tables now. So our V2 is root of 2 into H1 minus H2. So H1 value 2935.4 minus H2 is 2846.9. So here already we have seen it. This is in kilojoules per kg. We are substituting inside the root here. So we have to convert into joules per kg. Root illana no problem, but inside the root we are substituting it so that it should be in SI unit. That is kilos should be eliminated here. So we are multiplying with the 10 power 3 to make it as joules per kg. So it is common. Idukkum 10 power 3, idukkum 10 power 3. So that I have taken it as common here. So if we substitute our 10 power 3 here, that means if I am multiplying with 10 power 3, and if we are solving it, our V2 will be 420.71 meters per second. So this is the velocity at throat. 2 is at throat now. Now coming to our mass flow rate expression, m dot equal to A2 V2 by small v2 here. So the only unknown is our throat area here. Knowing our capital V2 and small v2 as well as mass flow rate is given in our problem, 0.2 kg per second. So now we have calculated our A2 as 1.547 into 10 power minus 4 meters square. Now finally we need to find out the exit area. Exit area is mass flow rate equal to A3 V3 by small v3. From this only we can get our exit area here. We should have V3 and a small v3 here. Now again in P3 already in 2 it is superheated steam. Am I right? So again still we do not know at 3 whether it may be a dry saturated steam or superheated steam. We do not know that. So again we'll check it with the steam temperature at 2 bar here. So again we have to follow the same procedure whatever we did in our previous steps. So the condition is 3 now. So I will write for the pressure P3 S3 equal to SG3 plus CPS into here ln or ln of T3 by T saturation. Now already we know that S1 equal to S2 equal to S3. So already S1 will be substituted in place of S3 here. So we need SG3. So for that we need to take our P3 equal to 2 bar here. So I will go to our steam tables now. P3 P3 equal to 2 bar. So we have to go back to our dry saturated steam table. And the S, F, FG, SG பார்க்கும்போது we have to ensure that you are seeing in saturated water and steam tables. Okay, Mama. So superheated steam table is separate. So for P equal to 2 bar, so we have 2 bar pressure. We need SG. So this is your SG here. It is 7.127. So it is 7.127 kilojoules per kg Kelvin. So I will substitute here. So already your S1 is 6.831. CP specific heat of the steam is 2.3 and ln of T3 we need it. So saturation temperature corresponding to 2 bar is 120. So it is 120.2 here. Now again we have to simplify this to get our. So how do you simplify? So ln I will keep this ln of T3 by 393 here. So in the right hand side we'll have 6.83 minus 7.127 by 2.3. So if I am calculating that value, so I'll get minus 0.1286. So we need T3 here. So I have to bring this ln on this side. So if I'm bringing this ln, so it will be inverse of ln. So that is exponential. So இங்க வந்து ஒரு e வரணுமா, exponential of 0.879. So it will be e power of 0.879 into 393. So if you do it in the calculator, so we'll get T3 as 345 point Kelvin. So it is 72.54 degrees Celsius. Now coming to our saturation temperature, it is 120, but your steam temperature is 72. So the steam temperature is less than saturation temperature. So the steam is, it could be a dry or wet. I hope you are following me. 72 on the definitely it is less. So the saturation temperature is greater than that one. So definitely the steam is either dry or wet. How do you find out dry or wet? For that we need X value. So that we are going to find it out now. So this is the procedure. We have to do it for all our problems. If you do not know, this is the way. Superheated condition we can verify with the steam temperature. Dry or wet we can verify with the X value. That you know that already we have done it in many of our problems. Still we see it. Okay, from the steam table at P3 equal to 2 bar. We'll take all HF, SF and a specific volume. So for the 2 bar pressure, so I have to take your HF, HFG3, HF, HFG3, and SF and SFG3, SF and SFG3, 5.597, 5.597. Similarly, we need to find out V3 also, small V3. So the VF and VG also we should get it. So this value and this value is VF and VG, VF3 and VG. So we get all the values now. So we have to directly take it out. We have to substitute in the formula now. So now coming to our calculating of X value. So S3 equal to SF3 plus X3 SFG3. This is the relation we know for the entropy. Okay, wet or dry saturated steam. So already S1 equal to S2 equal to S3. So S1 value I will substitute it here. So we have got SF and SFG3. SF3 is 1.53 and SFG3 is 5.597. So from this, if I am calculating my X3, so X3 we are getting 0.947. So already we have discussed that always our X value should be less than 1. Maximum it can go up to 1. If it is less than 1, then we can confirm it. The steam is wet steam of quality 94%, 94.57% dry. Remaining is, that is your 6%, around 5 to 6% is your what is that? Where moisture is present. Now by knowing this X3, so we can easily find out our H3. H3 equal to HF3 plus X3 HFG3 here. So H3 equal to HF3 is 504.7. So we have already got it. And X3 is 0.947 and HFG3 is 2201.6 here. So we can easily get our H3 as 2589.6 kilojoules per kg here. Okay. So similar to our H, yes, we can also write V also. When H equal to HF plus X HFG3 and S equal to SF plus X3 SFG3, V can also be written as V equal to VF plus X3 VFG. Okay, VF plus X into VFG. Here, one thing we have to see it here. Unlike our enthalpy and entropy in our steam table, we don't have VF, VFG and VG. We don't have it. We have only VF and VG. So that accordingly we have to change our relation. So VFG can be written it as VG minus VF because we know that Vg equal to Vf plus Vfg. Okay, that I'll show you. Okay, steam properties la. Okay, I'll show you that. I have one more relation. You see it here. Actually, similar to our H. Yes, we can write V equal to Vf plus X Vfg. So what is Vg? G means F plus Fg. Vg equal to Vf plus Vfg. So Vfg can be written it as Vg minus Vf. So here what I will write in place of VFG, I will write VG minus VF. Why we have written? Because in our steam table we have insufficient data. So we don't have the values of F and Fg. So accordingly we have to rewrite our relation to get our final answer here. So V equal to Vf plus X Vfg. Since we don't know the value of Vfg directly from the steam table, so we'll rewrite it as Vg minus Vf here. So accordingly we have written it as Vg minus Vf here. Okay. So in that way, already we have obtained our Vg and Vf. So I hope you are following. I think you understood this relation. Now your Vf3 and Vg3. So already we have obtained from our steam table corresponding to P3 here. So these two values. So I am substituting it here. Vg3 0.8854 and Vf3 is 0.00106. So, we're calculating because everything we know it here. Only the left hand side V3 only we should know here. So V3 is 0.838 meter cube per kg. Now knowing our H1 and H3, now we can easily get our velocity at exit here. V3 equal to root of 2 into H1 minus H3 here. So H1 is 2935.4 minus 2589.6. So we have to write in joules per kg. So multiplying 1000. 10 power 3 and V3 is 831.62 here. So mass flow rate expression A3 capital V3 by small v3 here. Mass flow rate is 0.2 and your V3 is 831.62 and small v3 is 0.838. So we'll get our A3 as 2 into 10 power 4 minus meter square exit area. So we have calculated the velocity at the required place and also the throat area and exit area. Okay. So just similar to the previous problem, Edama, there in our previous problem we had only dry saturated steam. Here we have superheated steam. So that accordingly we refer the steam table. So by knowing this condition, so in the usual way, so 1, 2, 3 entropy constant illaya. Appo entropy constant nale vertical varum, straight vertical, because your x-axis is entropy. Appo vertical line. So by knowing this condition only, I am representing 2 here. Otherwise, I would have brought the 2 here. I know that 2 is the superheated steam. So after knowing that condition, I am placing my 2 on the superheated state and also 1. So 3, I know that wet steam. In the curve kila vandutale wet la vandrum. Enga vandalum seri. Okay. So 1 is superheated, 2 is also superheated. So 3 is x value is there 0.947. So 3 is wet steam. That's why I have drawn this. This is only representation purpose to understand. Okay. So how what is the state of a steam in the HS diagram. In the diagram. Okay. So I hope you understood. So I think you are at the end of the class. Okay, ma'am. So if you have any doubt, please ask me. In the copy the next class copy panikalam, because you will not have time to complete this. Okay.
Sir, screen.
Yes.
Screenshot எடுத்துக்கலாமா sir?
Screenshot. இல்ல மாயிருக்கிட்ட பரவாயில்லை. Next week copy பண்ணிக்கலாம். Okay.
Okay. Okay.
Yes, here comes some of you asking me doubt. Tell me please.
Doubt, sir. H3 we are solving or not? That one.
H3 we are solving. We have calculated H3.
Okay, sir. Okay.
We have got. Then only we can able to get our V3. 25896. Okay, ma'am. Okay. So what I will do it, I'll close the class now. 5:30. Copy பண்ணாலும் முடிக்க முடியாது. Okay, ma'am. உங்களுக்கு 5:35 இல்லையா class next day.
Yes, sir.
Yes, sir. Okay. I'll close the presentation. So we have some more problems in that. Nozzles problems we'll see it. Next class another copy பண்ணிக்கலாம். Okay, ma'am. I'll close that. I'll take that.